In this paper, we present a novel structured light system using a line sensor. In a traditional structured light system, we obtain correspondences between columns of a projector with pixels of a camera. Once we obtain such a correspondence, we can intersect the plane corresponding to the projector column with the light ray corresponding to the camera pixel. This allows us to obtain 3D points on the scene. In the proposed design, we swap the roles of the camera and the projector. Now we have a 1D line sensor whose pixels integrate light along a plane in the scene using cylindrical optics. The projector has two angular degrees of freedom. Now, if we obtain correspondences between camera pixels and projector pixels, then much like traditional structured light, we can intersect the plane and the ray to obtain 3D scene points. However, note that the plane is defined by the line sensor and the light ray is defined by the projector. This architecture is the optical dual of traditional structured light. Hence, we refer to it as dual structured light, and it enables 3D scanning with a line sensor without the use of any moving parts. To obtain 3D scans of a scene, we scan one projector row at a time. The projector scans each row sequentially while the camera captures a corresponding 1D image. The image above shows the acquired data by the line sensor. The number of columns on this data is the number of pixels in the line sensor, and the number of rows is the number of rows of the projector. We repeat the same with other gray code patterns. Given all of these data points, we can find correspondences between camera pixels and projector pixels, and subsequently via plane ray intersections find 3D mappings of the scene. It's worthwhile comparing dual structured light to traditional structured light, where we obtain 2D images of the scene. Each such image has the same resolution as the camera sensor. By obtaining multiple images, with each image encoded by a different gray code pattern, we can obtain the depth map of the scene. Dual structured light is optically achieved as follows. We first use an objective lens to focus the scene onto the line sensor. Next, we carefully position a cylindrical lens such that the scene is completely defocused in the direction perpendicular to the line sensor. Here, we show a Zmax simulation of our optical setup. Notice how the light is completely focused along the line sensor, while defocused in the axis perpendicular to it. The temporal resolution of dual structured light is the same as traditional structured light system. Both systems require n-cube pixel readouts to obtain an n by n depth map using line striping, and n squared log n pixel readouts using gray codes. Here we show a hardware prototype. Notice that we have added a 2D helper camera to help with calibration as well as evaluate the accuracy of our system. The goal of calibration is to determine the plane corresponding with each line sensor pixels. Our calibration method is a 5-step procedure. First, using the helper 2D camera, we calibrate the projector and the helper camera using standard calibration techniques. Next, we place a plane in the scene and scan projector pixels sequentially. Using the helper camera, we can obtain 3D locations of these points, and further, by associating the points with line sensor pixels, we obtain 3D points in the pre-image of each line sensor pixel. By repeating this with multiple scene planes, we can find the plane corresponding to each line sensor pixel. Now, let's look at some results. Our system produces realistic 3D scans for a wide range of objects. For the scene with two balls, our dual structured light system has a performance similar to traditional structured light. The average difference in estimated depths is less than 2 millimeters. We observe the same for the scene, which is slightly more complex. Global illumination is often challenging for structured light systems. In this scene, we have a shiny bowl with a concave shape. Surprisingly, dual structured light works significantly better than traditional structured light. However, we note that the formal theoretical study of the effect of global light on dual structured light is beyond the scope of this paper. The scene involving wax objects has significant subsurface scattering, which adds to global illumination. Once again, dual structured light provides depth maps that are significantly better than traditional structured light. We conclude by highlighting applications of dual structured light. Imaging in shortwave infrared is one such compelling application. Sensors in shortwave infrared are prohibitively expensive. Here, a low resolution line sensor can offer tremendous reduction in the cost of the imaging system, without any loss in the resolution of the obtained depth maps. A second application of dual structured light is in the context of dynamic vision sensors, in short DVS sensors, where each pixel has the capability of detecting temporal intensity changes in an asynchronous manner. Prior work in this area has shown that structured light using DVS sensors can achieve benefits in terms of temporal resolution and better performance under strong ambient and global illumination. However, because of the complex circuitry at each pixel, high-resolution DVS sensors are difficult to manufacture in the 2D setting. And further, such sensors often have very poor fill factors. In contrast, a 1D DVS sensor does not have any such limitations, and hence, dual structured light using DVS sensors is a powerful application.